So it's my great pleasure to introduce you, Reda, to this series of seminars in probability and stochastic analysis in Técnico. Now it's joined with Brazil and Argentina, and a group of several universities in Brazil and Argentina. So I hope you'll enjoy the seminar. And so let me talk very quickly about you. I didn't have much time to prepare because my life has been a bit chaotic lately. But anyway, so Reda, you are coming from Toulouse, and you are an assistant professor in Toulouse, and you finished your PhD in 2012, right?
13.
So you have, oh, 13, sorry.
It doesn't matter.
Doesn't matter, but anyway. So, and you have many works in probability, many interesting works, and I really wait to see your talk. I think it will be very, very nice. So thank you so much for having accepted this invitation. Next time, let's cross fingers so that we can do it in Lisbon, in presence, in person. And you are going to talk about, okay, there is a title, I don't need to read it. And thank you so much. Go ahead, take your time. Okay, don't forget, it's 50 minutes and then 10 minutes for discussions.
50.
Thank you so much.
Okay.
Yeah, 50.
So thank you, Patricia, yes, for this very nice introduction. And, you know, I'm actually very happy, yes, like to be talking to people in Brazil and Argentina now. Wow, I mean, I've been to Argentina, very fond memories. And yeah, and so let's start this talk. So this talk is joint work with Joseph Najmdel, who's my co-author for all these endeavors with random matrices. And here, it's like this very barbaric title. You should just understand it as A equals B. A is this guy that I will define, and B is this guy, and it has something to do with the circle. So, you know, so that this is the main theorem of the talk, A equals B. And well, you know, so that then the goal of the talk is to introduce like these two objects here. And so like the first one, so this first object is A, which is this GMC gamma. So this GMC gamma stands for the Gaussian multiplicative chaos. And this is, sorry. So this is, so you can ask, yes, like what is this object? So this is a random select measure on the circle. So I'll be writing it d theta. And there's the word like, there's the keyword like Gaussian. So actually the only randomness that I'll be using here is a sequence, an infinite select sequence of random variables that are Gaussian. And the second object here, B, actually, so like what is C beta E N? So those are models in random matrices, and I will define them. C stands for Circular Beta Ensemble, and beta, yes, like is a parameter. And here, like the randomness actually is like will be something different. So this is also a measure, but I'll be doing something a little weird. So I'll be constructing some sort of projective limit of these guys. And the randomness I will use, you'll have a bunch of coefficients that will follow me during the entire talk, and they will be, so I think it starts 0, alpha 2, alpha 3 here. And okay, so this object is from random, so yes, like matrix theory. You can also, it's also very integrable. And this object here, yes, like has been constructed by Kahane, and well, it's still both objects are within the realm of probability, but this guy is more into, well, I would say like, you can say like mathematical physics, but more specifically in the conformal field select theory. And the goal of this talk is actually tell you, okay, those are two random select measures, and I will tell you that they're actually equal, meaning like that there's a coupling. So there's a coupling, and it's like the coupling is non-trivial. To just say, okay, anything coming from here, I can read from here, and vice versa. So that's the theorem, A equals B. So let's define like the objects. So first, as as some, appetizer regarding this equality. So this is an equality that I always find like very, very remarkable. And actually, okay, so I'll tell you why. So here, during my entire talk, I'll have my Gaussians. So they will be normalized a little differently. So here, I'll always, so they're complex, and I'll normalize real part and imaginary part in order to have variance a half. And the alpha j's that I just gave you a moment before, well, alpha j, well, here so I gave you the it's like the modulus, like which has so like this law, which is a beta random variable, and the phase, I'm asking the phase to be something that is completely uniform. Okay, so if phases are uniform, so like what I can do here. So here's an equality that shows you like the correspondence between this A and this B, this random like matrix world and this Gaussian world. And here I'm saying like the first Gaussian, you can recover it as this infinite series. So you can say, okay, this is, so infinite series, this is the sum from, this is the limit as n goes to infinity. So here I'm just rewriting this thing just in order to have this guy. So if I cut at rank n, since I'm adding terms that are that have invariant phase, this guy indexed by n is a complex martingale. You can compute the variance and find that it's bounded in L2. So martingale that is bounded in L2 converges. Okay, so this thing converges. And some people, yes, like might tell me, okay, but this theorem is not shocking at all because, martingale converging, I mean, the limit of a martingale should be a Gaussian because of the martingale CLT. And then I should answer, well, you should go back to class because, this is only like when the bracket blows up. So it's actually very rare to actually know the limit of a martingale. So I'm telling you this thing is like is a Gaussian, and actually I know no elementary proof of this thing, like beside going through randoms like matrices and everything. And every time I give this talk, so I promise if ever someone has an elementary proof of this as identity, I'm promising a Michelin-starred hotel, no, not restaurant in Toulouse. So you're free to try it, and I'm serious. Like I'm actually very serious about this. So any takers? I mean, it's like it doesn't have to be now, but
can I say something?
Sure. Oh yes. So like regarding questions, please feel free to interrupt me whenever you want, because the style in Toulouse is you get interrupted very violently. It's like this is how talks go.
Okay.
Like in Toulouse.
So it has some similarities with the central limit theorem. So
Yes.
I was wondering if something using characteristic functions, the Fourier transform of.
So I tried it, but because of the pair correlation here, if you write a Fourier transform, you can never separate it. So, I mean, and actually it's not a CLT because the CLT needs an exploding bracket actually. So this convergence is not a CLT. This is an almost sure limit. It is not a limit in law.
Yeah, I see.
So
Okay.
fundamentally something weird is like
more like Kolmogorov's strong law of large numbers, maybe.
Yes. Yeah. So it's more a random convergence. Yes.
Okay. Okay. Sorry. Thank you.
So if you don't believe me, so here's a proof. So you just pick this thing, pick a phase, rotate it, and take the real part. So I'm plotting a radial projection here. Like you see a beautiful Gaussian. It seems a little too exact for n equals like 10,000. So this is a very expensive way of computing a Gaussian, right? And then if you tell me, oh, well, bell shapes just look like other bell shapes. So here's a quantile versus quantile plot. So you see like everything fits so perfectly. This is a perfect line, even it's like on the edges. So this thing has to be true. So this is the numerical proof, which is just hand waving. Okay. So now it's like, in order, it's like not to treat just like the first Gaussian, which is here for k equals 1. I'm just gonna take all these Gaussians and package them into one single field. So this is a random function on the circle, random Gaussian slide distribution, where here the only thing I'm saying is that pick the Gaussian slide distribution on the circle whose Fourier modes are my Gaussians like divided by square root of k. And actually this is a distribution. This is not really a function because well, it's a Schwartz like distribution, because you have to dampen a little bit like the Fourier coefficients in order to be able to evaluate it. Because, well, if you compute like the variance here, it's like you get a so the variance of G, it looks like a sum of so like 1 over k. So this is so at a specific point. So this is plus infinity. So this is not a function, like it has no, but this is a distribution. And it's barely not a function because it is actually like in all the negative Sobolev spaces, because as soon as you dampen just a little bit the coefficients here, if you take like the power not a half, but a half plus epsilon, then you can compute a variance and everything works. So it is barely not a function. And in order to make it into a function, like the idea is just like to take the harmonic extension. Well, if you convolve like with the Poisson kernel, this G on the circle, you just add R to the power k to each Fourier mode. And here's a plot of the function on the disk. So inside the disk, the thing is very smooth. And here I stopped at, I think I stopped at 0.97. Because on the boundaries, like the function completely is like blows up and becomes extremely, you know, it's like chaotic, and it goes like up really high and down like really high. So on the boundaries, this is just the idea that we don't have a function. It's like we have a random slide distribution. Okay, so this is my functions. Like we just packages all the Gaussians, and this G I will see it on and on during the entire talk. So first, Kahane's GMC, the Gaussian like multiplicative chaos. Well, the short answer is, what is G? What is the GMC gamma? It's the measure that you obtain by exponentiating this field G. And here are so this slide is just for, sorry, I heard something. No. Hello.
No. I don't think it was. No, I think it's fine.
Okay. So okay. So this slide is just for, you know, it's like to scare you off, because, you know, so this thing looks scary, but, you know, so like this is just like the modern motivation. It's like why people like care about this GMC. So here's a very nice like theorem by like Miller and Sheffield. So here's so you sample like the Brownian map, and this picture has been given to me by Jérémy Bettinelli. So it's like, what do? You just sample a very large random map uniformly among random maps of size n. And what is a planar map? Just, you know, a so this is a quadrangulation like that you can draw like on a sphere. You ask like the computer, yes, like to put springs, it's like between on every edge, and you let it reach an equilibrium, and this gives you a nice like 3D picture. And that's like the picture you obtain. And this is a topological sphere. And what's interesting is that like this thing is it's Riemannian, by just saying that the length of every edge is 1, but here there's so many like edges that actually it's like the distance here is pretty long. But this is a topological sphere, so it's like uniformize it, and you throw away all the metric structure, but you keep the measure. If you throw away the metric structure and keeps like the measure, you can ask what is this measure, and the answer by Miller and Sheffield. So this actually in rather weak sense, but I don't know if this has been made better. But the answer is that this is a GMC of size, it's like with coupling constant gamma, which is this. Okay, so what is the message? Yes, like from this story here, that GMC gamma is the natural Riemannian measure on random surfaces which model Liouville conformal field as like theory. So I will just stop there, and I will tell you, if you want to know more about this, please invite the specialist. You know, I'm just you know. So I learned everything from reading very nice surveys of Rod and like Vargas. And I just managed like to understand this theorem by Miller and Sheffield. Okay, so we'll go back to our things. So today's talk is about something much more simple. It's in 1D, and so much more basic. And here I will just take, so I will take a regularization parameter R, which is, so I'll take, instead of taking exponential of G at exponential I theta, I will take it inside like this. So this thing is very smooth. So I can take the exponential, and I want to make sure that this thing stays in L1. So I will so I will normalize by half of gamma squared the variance. So this thing has expectation 1. And when I compute, because here like this variance here looks like a log actually. So it's a log of 1 minus r, so r square. And so you get like this pretty neat like formula. So this is a very nice invariant GMC. So so here, so it's like what happens here. So this function g like that you saw on the boundary, if r goes to 1, it can become really large or really small. And so the exponentials like will make it, you know, will make things like much worse. But luckily, it's like this thing goes to 0 as r goes to 1, so it dampens considerably the wild behavior of this guy. And you have a theorem, so that so this is like the construction of Kahane. Also, I recommend the very nice surveys of Rod and Vargas. And then, you know, if you want to learn like the topic and actually prove things, so there's a very nice paper by Berestiki. It's like Nathaniel, it's like Berestiki. So it's a paper in ECP that is extremely nice and really streamlines like the sort of arguments and proofs, and it's like makes it very, very tractable. So the idea is, okay, so you could just take GMC with this parameter R, you take a test function, you integrate, and then you take R going to 1, and you look for a conversion in L1 or in a probability. And you get a limiting object. It has to be a measure, and you know, so like you're fine. So this is like the easiest way of defining the GMC, but as you see, it's sort of untractable. So like you can argue, well, what are its properties? Where is it supported? Is it like non-trivial, so etc. So here you can ask like a zillion of questions, but I mean, here I'm just planning on defining things. So GMC, just like okay, it just basically, and this like you can so understand it. So sometimes like people just write it as the yes like integral of this thing, and then they just write, if you want a real yes like physicist notation, you see them like writing this. And it just means that, okay, this thing is not a function, but I so exponentiate it, and these 2 points that just means that I normalized it somehow. And that's the right way of doing it. So here's the objects like that sort of, it's like where I started with. So circular beta ensembles.
And for gamma bigger than 1?
Sorry?
For gamma bigger than 1, there is nothing, or it doesn't make sense?
For gamma bigger than 1, the limit is 0, actually. So actually, it's like the idea is that if you take gamma as like too large, the idea is that this thing like will have a certain like maximum, which will be exactly of the order of log of this guy. And actually, it's like this thing's like will go to 0 much too fast and completely crush it's like everything, and the limit will just be 0. At the critical setting, and if you ask me again, it's like what is the like critical value? I mean, so if you look in the literature, people like will tell you, oh, the critical value squared of 2D. square root of 2. Like, but here I took the normalization in order to make it 1, just because I'm lazy. 1 is the normalization. So 1 is the critical value. And actually for gamma criticals, like you can take a different normalization, which is not like this one, and you could get a limit. But for the supercritical regime, so I'll make comments so like in the conclusions at the end, because actually so that there's not a real let's say agreement on what people should do in the supercritical regime. I mean, so like the people who knows I mean, like Rod and Vargas, like I think like they know like what you should do. But okay, so let's go to the random matrices. So the randoms like matrices. So you've so I don't know how much you guys like have been hearing about it. So in randoms like matrices, yes, like what we love to do. So this is just on the circle. So I have my circle, and then I sample endpoints. And so I sample them like with the density that is proportional like to the Vandermonde to the power beta. So here you recognize my Vandermonde, and here this is just a normalization constant. And you can say, okay, this is just like a Coulomb gas like type thing, because you can always rewrite this as exponential beta Hamiltonian, and the Hamiltonian is, I guess, like will be the log of the pairwise interactions. So this is a Gibbs Coulomb gas on the circle. So if you ask, why is this a random select matrices? So here's a good answer. So like if you take beta equals to 2, you should recognize the Weil integration formula, like which tells you that if you pick a matrix that is Haar like distributed on the compact group, then the spectrum follows exactly this. And this thing is extremely rich in representation as like theory, and I've been brought like to the sub. I mean, so here you can put like a zillion names here. So like the works of Bump and Gambert and Borodino, Okunkov. So it's very nice. And for general beta, there's not really a random matrix models, but it's not as clean. And also, but still, people who like integrable systems are very happy. It's like with this object, because it's related to Jack polynomials, and which are also eigenvectors for an integrable systems called Calogero Sutherland, and there's some higher rep theory in relation with Cherenik algebras. So, but don't worry, today I'm not using any of this. Actually, so like this is a purely probabilistic work. So first, I'll define like the characteristic polynomials by just saying, okay, these points are the eigenvalue of a unitary like matrix. So the determinant is the product of over eigenangles, and it's this. So this will be the objects like that packages like all of them. So okay, so that's the model, and right away I can tell you, okay, so like this model has Gaussian limits as n goes to infinity. And here, actually, I'm very happy, yes, that Percy is part of the audience, because it's like this was one of my favorite select theorems when I started. So first of all, is that so the circular beta ensemble is a regularization of a Gaussian Fock space. So here, I'm not saying this is a CLT. And you understand why. Like I really, so like first, like when I started as a student, like people like often like told me, okay, so that's a CLT. No, I actually it's like disagree profoundly. This is not a CLT. So let's just go. Yeah. So I'm saying the C beta E is basically a regularization of a Gaussian space by endpoints, but at the level of symmetric functions. Well, so this is a complicated statement, but you can just look at this. So the trace of un to the power k. So this is just So I'm summing all, yes, like eigenangles. Which is sometimes, yes, like written, this is the pk, like the kth power sum. And I'm saying that this thing converges without any normalization, because here you should normalize by n. Again, without any normalization, like this converges to square root of 2k divided by beta of a Gaussian. So actually, this is a reinterpretation of the theorem by Strong-Zig, so the Strong-Zig theorem. There's a yes, there's a proof by Diaconis and Shashahani, like using Schur functions, and there's a proof by Matsumoto Jang, like using Jack like polynomials. So here I would like to give you a proof that I find like very funny. Actually, so I'm not claiming that the other proofs are uninteresting. Like this proof is not quantitative at all. I will give you. So like here's a proof that aims at showing you. So actually, so I have the book with me. So if you can see this book, actually this book, I aim like to convince you that this book is a probability book. So first you should open slide, and actually so this book contains the proof by just putting together a few things. So first you just, okay, so you look around and you're like, okay, there's the pk power sum select functions. And the p lambda is just like the product over these things, and lambda here. So that's a partition. Which is like you'll see, it's like in the book always like, yes, like written, you know, this is lambda 1, lambda 2, lambda 3, etc. So okay. And then then I define as a scalar product between functions in n variables, the expectation over the circular beta ensemble. So here I'm writing it's like a zi here, so like to actually say z1, z2, z3, etc. So first fact. So you open the book at I think it's chapter 6, subsection 9. So it's like the thing called another scalar product. There's like, it tells you, okay, this scalar product with the brackets and subscript n converges to another one. And this thing actually is called like the Hall-McDonald scalar products, like which has been studied in the entire book, and which uses infinitely like many variables. And actually, so here when I compute scalar product, I'm just computing moments, right? Because here I take p lambdas, I take powers. So I'm computing moments of these pks. I'm just computing, so this thing, I'm computing moments of these pks and the moments of the limits. And the moments of the limits, in the limit, these things are orthogonal, and there's a constant here. Okay, like, okay, what the hell? So like, is this constant? So then you go back at the beginning of the book and you're like, what the hell is this constant? And actually, if you look at it really in the eyes, you realize that this constant is nothing but the expectation of a bunch of Gaussians, where here's like the mk lambdas are the multiplicities of k in each of the partitions. So actually, McDonald like never says that, but McDonald proves that actually, I mean, the entire book is about like the scalar product. So the entire book is about like expectations of Gaussians. So, I mean, so that's a probability book. I mean, but it's more like interesting. Like then that's like, it's like this proof tells you that C beta En, you get it by restricting the space of symmetric functions to n variables. So basically, this is why it's like I'm saying that like the convergence of the traces to Gaussians, this is not a CLT, actually. And again, so I'll go back, yes, like to the proof of Diaconis and Shashahani's, like which has some other secret, yes, like ingredient, some like leftover mystery. So okay. So now, so that you know, the traces go to.
Before, can I ask a question, Reda?
Yes.
Hi.
Sure.
So you have a much stronger theorem. You have that all of those traces of powers are independent in the limit too.
Exactly.
I mean, right.
Yes.
That all the joint mixed moments. That's
Exactly.
what you showed. All the joint mixed moments are the same as the joint mixed moments of the limiting Gaussian. So it's very strong result. Yeah.
Yes,
nice.
and I take the advantage of adding also so that part of your proof is actually, so there's this very nice fact that for beta equals to 2, the moments actually match the moments of the Gaussian up to a bigger and higher order. So actually for beta equals to 2, like the convergence is much faster. And so I'll go back to that later. And it just in order to say that this proof is actually not quantitative at all, and there's this little extremely fast like convergence for beta equals to 2, so that I want to go back to later. So okay, so now so let's see the Gaussianity and the log correlation. So let's see that randoms like matrices converges like to this G function. So this is, okay, so it's like with this little like theorems, like we know that this guy converges to square root of 2k beta, and then my Gaussian, then I divide by k here. So then I get square root of 2 beta, and then my Gaussian divided by square root of k. So if I just replace everything, because, you know, as Percy said, you know, here you have convergence of the vectors, because all, you know, this is a moment. So the thing I presented to you was a moment is like method for all these things. So you believe that if you, so this convergence like happens as like in law jointly. So you believe that you have this convergence, that the log of the characteristic polynomial converges to this Gaussian field. Here, like there's no, it's sort of pretty expected, and it's a convergence in law, and this is my log correlated field G. So this is not a surprise. And a step further is to take this thing and build a measure from it that should look like the GMC. And so here's a result that is that looks very similar like to the story I want to tell you. But actually, the more like the talk like will progress, I hope you will understand it is fundamentally different. And the result here is by Nicolas, Saxman, and Webb, and it says like the following thing. Just take my characteristic polynomial. I know that it converges to somehow exponential of square root 2 over beta G. So, okay, I can just take a measure that is built from the characteristic polynomials. I take a test function. This thing is like exponential alpha square root of 2 over beta G, but here beta is equal to 2. And then I normalize it in order to have expectation 1. And it should converge like to GMC. So this is not a surprise. And again, this is a convergence in law. Okay. But here, I want to say that this theorem, in my opinion at least, has very little chances of being proven for other beta. So here I want to make a few remarks. So for beta is equals to 2, the convergence of traces like to Gaussians, so these traces to these Gaussians, this is actually extremely fast. Like I think like that was a conjecture by Percy, and it was proved by Johansson, like actually way before I even finished my thesis. So I don't really know like yes like the history of this problem, but there's a paper by Johansson that said that you have super exponential convergence for a very strong like distance, which is the total variation sled distance. So for beta equals to 2, actually this is much more doable than general beta, because this convergence is extremely fast, and this is not true for general beta. And here it's like we get to some conformal field theory. Beta equals to 2 is critical in some sense, a little bit like this gamma equals 1 is critical. So there's some criticality for beta is like equals to 2. And actually, like the story I want to tell you is not about a convergence in law. The story I want to tell you is non-asymptotic, and it's almost sure. Again, it's a little bit like this funny series that I told you about at the beginning. It is an almost sure equality for all beta, and via some non-trivial coupling. I mean, and actually, you know, this is, you could always say, okay, if I have conversions in law, I can always do some Skoroha type embedding, but these are empty statements. Here, I want to say something different, which is GMC gamma is, so when I say this, I'm really saying GMC gamma is an object that it's like you can cut into little pieces and have finite n approximations of it, which are exactly the random matrices. So that's the statement. And let's see how, yes, like we can make sense of this thing a little more precisely. Any questions?
No.
Okay, so the tool will be orthogonal select polynomials, random orthogonal select polynomials. And here, like, we can all happily go back to undergrad. And back in undergrad, like we were told, SLED, that if you take a probability, yes, like measure mu on the circle or on the line, and you just do Gram-Schmidt, it's like you obtain a bunch of polynomials. And these are orthogonal in L2, it's like with the measure. And well, on the lines, like this thing called like the 3-term recurrence, but on the circle, there's a simpler recurrence. It just tells you that the next one is Z times the first plus something. And this something is actually not that complicated. It is just like the same one where, so you have this ugly transform. So don't read this, like just forget about it. This star is just, you take the polynomial, you reverse and conjugate the coefficients. Just like, don't read this. So this is rubbish. And this equation is the same as the previous one where I just reversed and conjugated all the coefficients. So actually you have a much more simple thing on the circle. And here, like so the thing tells you that you have some coefficients here, alpha j, that appear, and that basically drive the entire recurrence. And well, here I told it that if I start from a measure mu, then I have a bunch of alpha j, right? And now we will see which are the alpha j's that are sitting behind randoms like matrices and select measure. And okay, so there's a very nice paper by Rowan Killip and Irina Slaknenshu, so that tells you that you can realize the C beta E as the nth coefficient of a recurrence. And actually the alpha j's are exactly the ones that I've given you at the beginnings, like the alpha j where so this in-law is a beta. So it's the same guys. So actually what the theorem tells you is that take the recurrence where you take these alpha j's, go through this Zager recurrence. So actually this is very easy. This is just, you can program it very easily. And then at step n, like you stop and you put one eta that is uniform like on the circle. And this is a pretty easy theorem like to prove. This is essentially like the computation of a Jacobian, right? You have a certain law on the alpha j's. Then when you do this, you get a polynomial. You look at its zeros, then you get a law on the zeros. Then you compute like the like Jacobian, and everything fits. It's actually very simple. But here there are two important subtleties, and unless someone asks me about it, I'm not answering them. I mean, you know, if you're like, oh, I really want to hear like the story, well, here it is. Two important subtleties, because here, if you compute like the dimensions, like they don't match. Here, I told you like the zeros, here you have n zeros. Here, the alpha j's, there's dimension 2n-1. So I've hid half of the variables under the rug. And if you don't mind, you know, just leave it there. More importantly, It's like the funny thing is this funny projective property. This projective property is actually, it's really funny because when you take the circular beta ensemble, it's like with n points, you're on the circle and you're putting points, right? And with some Coulomb interaction. But between n and n plus 1, why should there be any consistency? It's like, why should n plus 1 points share the same first alpha j coefficients once you use this re-encoding? There's no reason. So when you look at it, like something is happening there, and actually you could say, so you could argue from a, I mean, once I heard a physicist like tell me, oh, well, you know, it's a Coulomb interaction, so it's electrostatic. So if you believe that the world is well made, if you add one more point, then, you know, things should somehow be as like consistent. Well, you know, it's a, okay. So it's a little bit of a religious argument. You know, here I'm doing something very less like concrete. So the consistency is there's no reason for C beta En to share the same alpha j's at the beginning as C beta En. And actually here I'm lying to you because actually in the original statement, the order is reversed. So you have to flip them over and, you know, you have to do a little question. So once you observe this consistency, it's like that was like the question. It's like that we asked when we started like the project. It's like with Joseph. We were like, okay, we have a bunch of coefficients, alpha j's, that we get from a measure. They're all like consistent. You can take C beta En 1, 2, 3, 4, and you get all the coefficients. So you basically put this C beta En's like together. So you look at some projective limit. I mean, here, when I say projective limit, I don't mean anything fancy. I just mean take all the coefficients. And you can say, okay, is there a measure so like behind it? Does it come from a measure? So this is a theorem from 1930. So 1930, so for people who know, who like orthogonal polynomials, like the thing, people who cite, like there's a similar theorems like on the line due to Favart, and this is always like the cited one, but Favart came afterwards. So funny. So, you know, life is unfair. So I guess so like this is part of re-establishing some fairness. But Favart on the line came actually after Verblonsky. So what is the theorem? So I take probabilities like measured on the circle, and I gave them the weak select topology. And here Dn, so I take all the coefficients that are appearing this Zeger recurrence, and if I go say this way, can I come back? And the answer is yes. This is a homeomorphism, so it's invertible, and better than that, it is continuous. So here you have weak topology. Here I have pointwise, and actually you can ask like why you have this weird thing, because actually if I start with something atomic with atoms. Here I fall here, and the recurrence stops at step n, because well, you have n atoms. It's like you can't build so your Gram-Schmidt process stops because L2 of the measure is a finite dimensional vector space. So then you get like this questions like that we asked at the beginning. We were like, okay, this is weird. These are consistent, so let's put just all of them and call this measure the projective limit of C beta En. I just put all the coefficients. So this is a fair name, right? You just put all the coefficients. And this thing, actually, if you look at the literature on orthogonal polynomials, this measure will be the thing whose quadrature points, you know, so like if you do like doing numerical analysis, you like to find what are the endpoints if I want to take a measure and approximate it by endpoints such that the thing has the same 2n for first moments. This is called like the quadrature points. So, and I'm asking like the thing whose quadrature points are the C beta En. What the hell is this measure? So I already told you it's GMC. So that's the theorem behind like the title. So if we are in the subcritical regime, take the measure, the projective limit of C beta En. So you just put all the coefficients. And and you take the GMC and you renormalize it into a probability slack measure. So the theorem is that this is the same object, actually. And you could say, okay, that seems okay. Just take exponential g and you go to the limit. So I told you, well, here, I mean, it's like the proof doesn't do at all like the same thing as Saxman, Nicola, and Webb. And you can also try saying, okay, maybe you have approximation theorems in orthogonal polynomials. Well, so here's a funny thing. Actually, all the theorems that we found in the deterministic literature just don't work, because GMC is outside of the scope in terms of regularity. It's an ugly slack measure, and it's like nothing works with it. So we were like, okay, so that should be easy, but it wasn't. And okay, so here's something theoretical that you could do theoretically, but I would be very happy to actually see it done. You could theoretically, sample a GMC, say, okay, here's the measure. Then you can start doing some, a quadrature thing, just run like the packages with the, that find, best approximating points for approximating like measures, etc. Just run them. And if you run these things, it should give you random matrices. So, I mean, this is just a theoretical game because frankly, sample GMC. So how do you do this? Then start, running like the known algorithms on it. So here are the ideas of proof. So this slide is a little chunky, but don't look at it like too much. Just like vague details. So the philosophy is, okay, I have a parameter here. So like, which is, so here I have a parameter R. So here R goes to 1. Then I end up like on the circle. And here R is 0. And here I use finitely, so yes, like many Verblonskys, finitely many coefficients. And here I use all of them. So the idea is just some introversion of limits, right? You just start from a measure that uses not all the coefficients and that uses something inside like the circle. Actually, a tricky thing is to find the correct normalization select for this thing, select to be of this shape. So it's the nth orthogonal polynomial, a little bit inside like the disk with just n guys. And yes, so when you take R goes to 1, you normalize it in such a way that you obtain like this measure. This measure is actually pretty important in approximations like theory. This is called like the Bernstein-Zeger approximation. And this thing just converges to the measure that uses all the Verblonsky coefficients. This is just general select theory. So this is free. And then you're like, okay, I would like to go like the other way and actually prove that here I should get some GMC and actually say that these things are equal. So first, so what you do is like, okay, maybe I will use like this. I will put, so here this is proportional to. So here I put the right thing in such a way that this thing is a martingale once I integrate it against a function. So this way I get a limit. And in this limit here, I will recognize like this Gaussians, because here I've put all the Verblonsky coefficients, and here this characteristic polynomial would actually converge almost surely. This is not a convergence in law, a little bit in the same spirit as the remark I gave you with this first Gaussian being equal to a sum of alpha j's. And here I get the GMC. Then I get some random constant, and then I get something actually that is very ugly. There's some really nasty thing here that I need to prove that when R goes to 1, it disappears. Okay. So the difficult points is that like the filtration by Gaussian and Verblonskys have bad overlap, and this WR, you can put we can write some Doob decomposition of it with respect to the filtration of Verbolunski's, and it has a non-trivial limiting SDE, which is very ill-behaved. But it is, and this is actually, yes, like what we need, because since it's ill-behaved, it will somehow forget its starting point extremely quickly, because it will have some sort of, it's like entrance law. And since it will forget everything right away, the limit will be somehow, it will average out and it will disappear and will just count for a constant. So here, this is just very hand wavy, but like it's, yeah, I mean, yes, like we did whatever works. So more perhaps like more it's like interesting. Yes, like I could tell you, it's like, okay, why should you even care? I mean, okay, why care? Because, well, I was told yes that I should care because, yes, like some people asked questions. So consequences. So the funny thing is that it's like you can couple all random like matrices from one single GMC gamma. So this is funny. Another question was asked by Balind Virag at the ICM 2014 in Seoul. I think in English you pronounce it Seoul. So so he said, but more in the context of the real line R. So here we did it in the circle. So he sort of understood that GMC gamma and this measure should have some similar features. So he asked like the question, well, could you at least prove that they have the same like multifractal spectrums, like which is features of these measures, because like these measures are very fractal, so they have something called a multifractal spectrum. Well, I don't have to tell you like what multifractal spectrum is, in order to prove that they have the same like multifractal spectrum. If A equals B, well, they have the same multifractal spectrum. So this is a funny way of answering a question without really understanding that question, So so that's the second thing. So the third is so there was a conjecture by Fyodorov and Bouchot, which was about like the total mass of the GMC. And actually, so there was a proof given by Guillaume Rémy, who's a student of Vargas, a really bright young lad who proved it like using some tools from a conformal field as like theory. And so this gives you another proof. And actually, it's like as a side product of our proof, like you have this neat like formula. And it's like you just compute like a Mellin transform, and you find like this is an exponential random variable, and that was the conjecture of Fyodorov and Bouchot.
Can I question about that formula?
Mm-hmm.
Can I ask a question? Sure. In that formula, so are the alphas random? Are they beta? Are they your betas? Ah, I see. So it's the first equality is an equality in law, so
it's like this is by the construction. If you
right, I see.
But yes, like by proving that this thing is so as a byproduct of the proof, we recover the coefficient of randoms like matrices inside like this guy. So this thing is just an explicit constant like that comes as a byproduct of the proof. These are the betas, and here beta over 2j plus 1.
Great.
So you just compute the Mellin transform, and you find, and actually then so something cute. So if you compute the Mellin transform of this guy, you recognize the Euler product for the Euler gamma function, which is the Mellin transform of this thing.
Wow.
It is a one-line proof, but it's cute. I mean, And then beyond the Fyodorov Bouchot, so like you can actually, there's a relationship relating. So if you say that the 0th moment is the total mass, the first moment of the measure, the first Fourier mode, second Fourier mode, etc., you can also express them like in terms of, so so you can have some more information about the like measure. Okay, so we were pretty happy about this, but but of course, it's like math never ends. So this is the slide where I tell you, yes, it really does like never end. So here I'm just throwing things at you guys, and if it brings questions, just go ahead. So the first question is, what happens in the supercritical phase? Because I didn't say anything. And people who work is like in this area, because you have this idea of, if gamma is too big, you have freezing, the thing goes to 0. As I mentioned, I had the question about gamma bigger than 1. That's freezing. And but when you make the construction using beta, there's no freezing. It just means that there's some funny normalization that actually carries. And there's a conjectural answer that we don't really have an answer to, and this should be this thing called the KPZ dual select measure. So this thing I'm not going to mention. So there's some work on the maximum of the field of characteristic polynomials. There's some funny question. So this is a question I really deeply care about. But so actually, okay. So here, this is a project where we didn't play at all with the algebra. So, and C beta E has an intimate relationship with the algebra. And actually, and when you read the CFT, there's this, like the first works of Victor Katz, vertex algebra. There's a lot of, it's always like the same things, like you have Jack polynomials like showing up there, but I frankly cannot relate. It's like the thing. So here, so there's probably some investigations, yes, like some works, yes, like to be done to actually bridge like the two worlds. Also, there's a relationship to conformal growth, because, well, CFT and conformal growth are just, it's the same thing. And you have some papers of Cardi on multiple SLEs and Calogero. And then the most troubling thing, like for me, is a question to like physicists, and perhaps, so I didn't expect like Percy's like to be here, but actually, you actually see that beta equals to 2 is special, because beta equals to 2 is critical from the point of view of the conformal field theory, from the point of view of the statistical select physics. And I always hear the physicists saying, well, when something is critical, special things happen. There's some algebra, etc. And at beta equals to 2, there's this extremely fast convergence of traces, this super Gaussianity that is happening there. So this is very like puzzling to me. So like this is, so I was mentioning this, yes, like this theorem of Diaconi-Shahshahani that actually tells you that this convergence is actually extremely fast. This convergence of traces like to Gaussians is extremely quick. So for me, this is like, it's like there's some fundamental thing like to understand there.
Thank you, Reda. Thank you so much. So let's thank Reda properly. If you can just unmute yourself. Thank you. So are there more questions from the audience?
So I have some question about the case where, so in the case gamma bigger than 1, you don't expect that you have some equality between the C beta E and the GMC gamma, because you said the GMC gamma is vanishing, and so, but you say that
okay. So the thing I'm saying is that one definition of the GMC gamma is vanishing.
So you mean you can take some different normalization in order
exactly. So there should be a different definition, which is actually like this one. And well, so I spoke to Vincent Vargas like quite a little, and well, it's like this. So I think we have the candidate. Like the only question is why this guy is natural. So like so let's just say that for GMC gamma. So okay, so you have one construction of this guy, which doesn't go to 0, but this construction, frankly, I don't understand. I mean, it is easy to understand, but it's made with some phenomenological considerations somehow, So I can tell you about it. So basically, GMC gamma for this guy, so like you can say, okay, so I'm going to take a Poisson select measure with a random intensity, and the intensity is the gamma that is dual, like with respect to this KPZ duality property. You can say, okay, that's what the physicists like tell you to do, and it should be the same thing. But you know, I'm just you know, so like, why would you do this? Where does it come from? And we're pretty sure that the C beta E gives that object because, you know, first moments match that thing. So, you know, so I think that, you know, so that the problem is not really like the random slide matrices. For me, I need like to sort out why people build this GMC gamma with gamma bigger than 1, and they do this KPZ like dual trick, and I don't understand it. So okay, so I know that here some people are very fascinated by KPZ, but you know, it's here it's this is like the other, it's like KPZ. Sorry, guys.
The real one.
I mean, I have no religion regarding this business. Kiznik, Polyakov, Zamolod, Chikov.
And for gamma equal to 1, you have a different normalization also, no?
Yes, but that thing actually, I mean, so that thing's like we have it actually. So we have the critical case for a very dumb reason, is that okay, so this is dumb. I should not have done this. Yeah, so this is, yes. So like, just because actually everything in our proof, everything is very it's like continuous in gamma and beta, so you just go to the limit.
And the phase relation between the GMC gamma and the C beta E, it was not known by the physicists before, because in the conjectures of the physicists that presented by Bouchot,
yes,
so they obtained this formula, but by some different way.
Oh, so, yes. So I can tell you, yes, the technique is very simple. So you take it's like this measure in terms of limit of exponentials of Gaussians, and you take moments. So you just use the standard replica trick. So you take this thing. So it's to the power k. So it's a k-fold select integral, and you swap, you know, expectation and k-fold as an integral, compute expectations of exponentials of Gaussians, and then you actually can compute moments of this thing. The problem with this method is here you're going to compute k moments of this guy, and k moments of this guy. Well, you know, exponential with the negative power, so you can only compute finitely many of them. But you already, I mean, it's like the conjecture is, I mean, it's very easy to understand, because here, if I put a k here and compute like the expectation, this will be finite as long as k is smaller than beta over 2, strictly. So you cannot identify a measure, I mean, a distribution from finitely many moments, right? So yeah. So that was the conjecture. So it's pretty easy to understand, but there was no relationship to random matrices.
Are there more questions from the audience? No. So Reda, thank you so much for accepting our invitation and for this very nice seminar. So next week, don't forget, we have so every week we have this seminar. So next week again at the same time, we have Alexandre Godelier from Marseille. So I hope to see you all, and thank you so much again, Reda. Bye-bye, see you soon.